Hello, it's time to start our next chapter. We're starting chapter 7. Chapter 7 is going to be all about exponential and logarithmic functions. Specifically, today we're talking about graphing the different kinds of exponential functions. You should be focusing today on the difference between exponential growth and exponential decay and being able to compare and contrast those two things. So here's the vocabulary that you'll see as you go through. So as we talk about each one, make sure that you make a note to yourself that you've checked off that you would be able to define or understand each of those terms. We're starting out with exponential growth functions, okay? Exponential growth functions look like this. F of x equals b to the x. So notice my x, my variable, is in the exponent. That's why it's called an exponential function. And in this case, b, which is the base of my exponent, it's a number, is greater than 1. So we're going to be specifically focusing on functions like 2 to the x, 3 to the x, 4 to the x, where the base is larger than 1. When the base is larger than 1, my function will grow exponentially. This type of graph is continuous. It's 1 to 1, meaning no x's or y's repeat, and it is always increasing. So as we go from left to right, it's always getting larger because it's growing. Its domain is all real numbers. I can plug any kind of number I want in for x, positive, negative, fraction, decimal, anything. And its range is all positive real numbers. So if you look at the graph here, my graph gets really, really close to the x-axis. That means that the x-axis is an asymptote, a line that my graph approaches but never touches. It gets infinitely close but will never actually touch 0, so its range is all positive real numbers, or y is greater than 0. And its y-intercept is the point 0, 1. All right, so let's take a look at y equals 4 to the x. We're going to graph this function and then state the domain and range. So basically what we're going to do is we're going to make a table of values and connect them to make a smooth curve, just like we would with any other graph. Make sure that we plug in some negative values, 0, and some positive values. So here when I plug in -2, I'm plugging in 4 to the -2. Remember that a negative exponent means reciprocal, so that's 1 over 4 squared, which is 1/16. When we plug in 0, anything to the 0 power is the number 1. And then you can see here how we've plugged in the rest of the values. So that gives me 5 ordered pairs that we're going to graph. Then we come over to this graph. Notice here's the point 0, 1. Here's the point -1, 1/4, -2, 1/16. Obviously, we're estimating. Here's the point 1, 4, and the point 2, 16 doesn't fit on this graph. But you can see the exponential growth shape. It starts out growing really slowly. It's really low. Then it starts to grow faster and faster and faster, and it shoots off to infinity. The domain is all real numbers, and the range is all real numbers. So I want you guys to try this next one. Okay, your answer here should be C. And this is what your table of values should look like. Notice what's happening is that to get to each next y value, I'm multiplying by 3. 1/9 times 3 is 1/3. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. So unlike linear functions where we add the same value between each y, in an exponential function we are multiplying by the same value. That's why we get the curved shape. All right, let's take a look at some ideas of transformations with exponential functions. If I add or subtract a value outside of the exponential function, just like it has always been, it's a vertical translation. So it moves that many units up or down. Up if it's positive, and down if it's a negative. This h right here, if I'm adding or subtracting anything to my x inside of the exponent, what happens is it moves it left or right. So if it's x minus 3, it would move to the right 3. And if it was x plus 3, it would move to the left 3, just like the transformation rules have been all along. And then a, if I multiply anything outside of my exponential function that's not 1, if that's a negative number, I'm reflecting my graph over the x-axis. So that would be like y equals -2 times 3 to the x. I would reflect it over the x-axis because of that negative. And then if a, the absolute value of a is greater than 1, that's a vertical stretch. So this would be reflected over the x-axis and then vertically stretched by 2. And if what I'm multiplying by is between 0 and 1, ignoring the negative, then it is a vertical compression. So let's take a look at this graph transformation. 3 to the x minus 2. So first of all, I notice that I'm subtracting a 2 outside of my exponent. outside of my exponential part, sorry. So this is going to be a translation down 2 units. This graph is going to be 3 to the x like we graphed in your check your progress, but it's just going to be moved down 2 units. So when I plug in -2, for example, right, that's really 1/9 minus 2, which gives me about this value that they have here. When I plug in -1, 3 to the -1 is 1/3, but then I subtract 2. When I plug in 3 to the 0, I get 1, and then I subtract 2 to get -1. So it's taking every original value that I had and moving it down 2. So what happens in my graph is that now this line, y equals -2, is now my horizontal asymptote. It used to be the x-axis, right, which is y equals 0, but that also got moved down 2 units. So now my new horizontal asymptote is y equals -2, which determines my range. So here my range is y is greater than -2, but my domain is still all real numbers. All right, so let's look at an example here where I'm subtracting something inside my exponent. So this is inside the function. So since here I have 2 to the quantity x minus 1, this is going to move to the right 1 unit. Remember, when it's inside the function, dealing with the x, it's opposite of what you'd think. So x minus 1 actually moves it to the right 1. And so here they're showing you the work of how to plug in the ordered pairs. If you need to pause the video and take a look at that closely, do so. But this is what my graph would look like. So this is moved to the right 1. So the point that used to be 0, 1, right, on my original graph, this is my y-intercept, is now moved over 1 unit to the right. So that point is now 1, 1. Notice the x value changed and moved 1 unit to the right. And all of the points that would have originally been on 2 to the x have been moved over 1 unit to the right. For another example, in my original parent function, 2 to the x, 2, 4 would have been a point, but that point is now moved over to 3, 4. So the x coordinate got moved 1 to the right. All right, I want you guys to try this one. Make sure you identify the vertical and the horizontal shift. All right, your answer here should be A. In this particular graph, this +3 moved it up 3 units, and the -2 moved it to the right 2 units. So you can see here that my horizontal asymptote is moved from 0 to 3. And then my intercepts, or all of my other points actually, have been moved to the right 2. Sometimes it helps me to think about, okay, in the original function, 4 to the x, the point 0, 1 would have been my y-intercept, right? Well, this is the graph, part A, where it got moved up 1, 2, 3 points, and to the right 2 units. So it went up 3 and to the right 2. So that helps you identify the graph. All right, sometimes we model exponential growth, particularly in like population or interest problems. It has a constant % increase over a specific time using this function. A of t equals a times 1 plus r to the t. A, lowercase a, is our initial or our starting amount. R is the % of increase. Make sure you write that as a decimal, not as a %. And t is the time. 1 plus r, 1 plus the % is called my growth factor. That's my how much it's growing basically each time. Okay, so let's take a look at this example. It says in 2006, there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% per year, or annually. Draw a graph showing how the number of users would grow from 2006 to 2016. So here, 10 years are passing if that rate continues. So we're going to plug into our formula. Right, remember our formula is A of t equals a times the quantity 1 plus r to the t. So A, our starting amount, notice here that they're, instead of writing out 1,020,000,000, they're changing it into a decimal. So A here is 1.020 billions, and we can do that. My rate here is 0.195, but remember here in my parentheses I have 1 plus 0.195. So that's where they get this 1.195 here to the t. Then I'm going to graph my equation in this case because they're asking us to draw a graph. My graph here looks like this. This is showing you the growth, and it shows you where we would be in 2016, which is at about 6 billion users. But the key here is making sure you write your equation correctly so that you can get your graph. When you're graphing this, t is going to be like your x value, t is going to be time, and then y will be the total population. All right, now we're going to talk about exponential decay. So instead of something growing exponentially, it's going to decay or decrease exponentially. In this case, b, the base of my exponential function, is still positive, but it's between 0 and 1. So it's a fraction greater than 0 and less than 1. It's still continuous. It's 1 to 1, but of course this time it's decreasing because it's decay. The domain is all real numbers. The asymptote is still the x-axis, and the y-intercept is still 0, 1. But notice the shape. It starts out really high, and it decreases really fast, and then it starts to decrease slower and slower and slower. So let's take a look at this function. Y equals 1/5 to the x. So here's my table of values. Again, remember, 1/5 to the -3, when I plug in -3 for x, that is a reciprocal, so that makes it 5 to the +3. That's where we get 125. Then I go down to 25, then to the square root of 5, then to 1, because here they're plugging in -1/2. Then I get 1, 1/5, and so on. You can see as they're plugging in along the way. Notice that to get from -3 to -2, I'm dividing by 5, or multiplying by 1/5, right? So only 1/5 of my amount is remaining each time, so it's decreasing very rapidly. And this is what my graph would look like. Here my domain again is all real numbers, and my range is y is greater than 0. Notice my intercept here is still 0, 1. At the point -1, I have 5. At the point 1, I have 1/5, and so it gets really close to the x-axis really quickly. Okay, let's take a look at this one. This one is going to involve some of the transformations we talked about. So this +2 outside of my function means it's going to move up 2 units. This -1 here means it's going to move to the right 2. And then this 4 is going to be a vertical stretch of 4. And the negative is a reflection over the x-axis. So this graph has a lot of stuff going on. It's a transformation. My parent graph here would be 1/2 to the x. And here they're going to write out each parameter. So the negative sign in front is the reflection in the x-axis. 4 is that a value in front. It's being stretched vertically. H is 1, so when I do x minus 1, it gets moved to the right 1. And then k equals 2, translated up 2 units. So see what this looks like here. Okay, here I tried to draw you a graph of the parent function, y equals 1/2 to the x, so that you can compare. So first it gets flipped over the x-axis, so it would be here underneath the x-axis. And then, so if we imagine this point specifically, so that point gets flipped down from 0, 1 to 0, -1, and then it gets moved to the right 1, up 2, and then vertically stretched by 4. Okay, so it's a little hard to visualize when we're not writing out the whole table of values, but this is what your graph would look like, and we'll practice that more. All right, so try this one. Okay, your answer here should be A. And here are the different transformations you should take into account. It should have moved down 3 to the right 2, been reflected over the x-axis, and vertically stretched by 6. Okay, just like with exponential growth, we have the exact same, almost, equation for exponential decay, except I do 1 minus my rate instead of 1 plus my rate. But otherwise, my variables are the same. A is the initial amount, R is the percent of decrease, and then 1 plus R is called my decay factor. So let's at least get this equation set up here. My initial value here, it says the pressure of the atmosphere is 14.7 pounds per inches squared at the Earth's surface. And it decreases by 20%, so here's where they have the 0.2, for each mile of altitude up to about 50 miles. So again, this is decreasing, so 1 minus 0.2, 14.7 is my starting amount, and then t will just be my time. And here they're asking me to graph for the altitude from 0 to 20 miles. And this is what our graph would look like. So be careful here because t is actually altitude, not